Hello friends, good morning once again. I believe you have a better day before now, and I wish you a better day ahead. All right, friends, before I start this class today, I would really like you to like, subscribe, share the videos, and if the content is making any sense to you, all right, please don't fail to comment your opinion or observations in the video. It will make the work to go better next time. The next video is coming. Don't fail to share it with your friends and don't fail to like it. All right. In today's problem, we want to solve this geometry problem. This geometry question says we have this diagram here, and we have the equation behind the diagram here. And we're going to solve this problem. I've taken time to bring down the theorem behind this problem is this one. I'm going to tell you why I say so. So why I'm saying this is because for you to solve this problem, some people may rush to think that they're going to use alternate segment problem or angle at the tangent point problem. And I'll say, no, that's not what you're going to use today. You use something different from what you're thinking. The problem centered completely on the tangent principle. And for you to really answer this problem, you must understand these two theorems, the tangent theorem and this other theorem. Yeah. So this tangent theorem says, let's take a look at this theorem here and let's analyze this problem before we start to apply it to the problem we have here. So the tangent problem we are having here, you might have some days ago, see a question like this or in your textbook. If you have a diagram like this where, let me call this R, S, T, you can say U and V. Now, RST and UVT or VUT, these two lines are tangents because they touch the circle at the point S and U. So this circle has a center O. So the theorem here, without wasting much of the time, says that the line from the center of the circle, that is the radius, is perpendicular to this tangent at this point. That meaning that it's making an angle of 90 degrees with the tangent then. Similarly, it's making an angle of 90 degrees with the tangent here. And if I produce a line from the center of this circle outside to meet the angle theta at the point C. Now, this line that I produce, the line OT, divide this angle into two equal portions. That is, each part of this will be theta over 2 and theta over 2 respectively. So, but first, I would also like you to look at each part of the triangle form. I'm talking about triangle, either OST or triangle OTU. I want you to observe that these two triangles are right angle triangles. So for you to solve to obtain the value of the angle here, which is going to be similar to this one here, you will have to use the right angle triangle principles. And I also want you to observe that the two triangles I just mentioned earlier, the OST and triangle OTU, are both similar triangles. They have something a lot in common. This other theorem here is not really much. This theorem is telling us that when a line comes directly from the center of the circle, and this line meet a chord, let me call this chord MO. If the line meet this chord, well, let me say MQ, because I like to title the center O. The line from the center of the circle meet a chord at any point on the circumference of the circle, as you can see, like this. This line make an angle of 90 degrees, or we can say is perpendicular to the chord. Having these two ideas before we start looking at the problem is more and very much essential. So now I will read the problem. I believe you can also see the problem. In the figure, this figure, the pink color, PQ, QR, RS, and SP are tangent to the circle A, B, C, D respectively. So you can see the circle there, A, B, C, D, and we have some tangents there. Angle SPQ equals to 118 degrees, RSP equals to 80 degrees, and RCB equals to 61 degrees. We have to find the sizes of the angles in the quadrilateral ABCD, meaning the quadrilateral that is inside the circle here, ABCD. So to answer this question, let's move straight to where I've done some analytical work here. In the original problem, you don't have the center here. So the first thing I've decided to do is to locate the center of the circle and produce a line from any of these 2 points, like this. So that while I'm doing this, we have an angle at the external point of the circle, just like we have an angle theta from an external point of the circle. And then we have the radius OS and OU. Don't forget, we have right there OS equals to OU because both of them are radii of the circle. So here we don't have the radii. So if you look at the center, for instance, and produce a line, and then produce a line like this. These two lines, if I say that this is my center O, these two lines are radius or radii of this particular circle. So you have the right to call this R. R. The reason is the line from the center of the circle to any point on the circumference of the same circle is the radius of the circle, and they have equal magnitude or length. Similarly, we have an angle here. So I'm going to also produce a line from the center of the circle to meet at this point. Don't forget that where that line is meeting or is touching the circle is a tangent point also. So from that point, you can see that the line will make an angle of 90 degrees or is perpendicular, just like this theorem says. So making an angle of 90 degrees here, making an angle of 90 degrees here, making an angle of 90 degrees here, making an angle of 90 degrees here. as well. So having known that this place here is 61 degree, and from this line down to this place supposed to be 90 degree. Let me take you down. Okay. Knowing that from that diagram, look at a similar diagram here. Here to the red line is 90. Here again, down here is 90. But already we have that from here to the pink line here is 61 degree. So you can also see that to complete this place, the angle that can fit in here, this remaining angle, because this 90, this other 90 is on this red line here, the radius OC. So from here down to the tangent SR is what we call 90 degree here from here to here. So that means this other angle is going to be equals to 29 degrees. That angle is going to be equals to 29 degrees. Meaning angle ACB equals to 29 degrees. How I got that is, you have that 90 degrees minus 61 degrees, of course, is 29 degrees. Also, if you look at this quadrilateral form, we have quadrilateral. I want you to note that we have something quad C O D S. C O D and S. And we also have another quadrilateral, which is D O A P. So look at it. 1, 2, 3, 4. Having an angle of 80 degrees from an external point and an angle of 118 degrees from an external point. So remember, this law says if a line comes from the center of the circle down to that external point, it will definitely divide the angle at the external point into 2 equal portions. So that means if I produce a line from an external point to meet at the center, that means here is going to be 80 divided by 2, and we have 40 degrees. And here also is going to be 40 degrees, since these 2 triangles are similar triangles. And we also knew earlier, I explained that here from the core radius here down to the tangent point is 90 degrees. So if here is 40 degrees, here is 90 degrees, that means it's possible for us to obtain the value of the angle at this position, because that triangle form is a right angle triangle. So we say angle COS must be equals to 90 degrees minus angle 40 degrees. And 90 minus 40 will give you 50 degrees. Meaning here is 50 degrees. And here, since these 2 triangles are similar triangle, must also be 50 degrees. Again, I want you to consider triangle. If you consider triangle COD. From that same quadrilateral, COD. Look at the triangle. I would like you to observe that this length, OD, is equals to OC. These two lines are equal because they are radii of the circle. For that reason, it means that triangle, meaning that this particular triangle COD, is an isosceles triangle, meaning the base angle here and this place here, let me use another ink there, meaning that the base angle here and this other one here are equal. And how do we find that? To find that angle here, let's just call that place X to make work easy. So if this place is X, this place must be X. So that means 2X plus the angle here is 50 plus 50, that is 100, must be equals to 180 degrees. The reason is these are sum of angle in the triangle. Sum of angles in the triangle COD. Meaning X must be equals to 180 minus 100 divided by 2, and that is 80 divided by 2, and that is 40 degrees. Of course, angle X now is 40 degrees. Looking at this other side, so we have X there is 40 degrees. So just know that this place now is 40 degrees, this place is 40 degrees. So that means angle C is completely gotten. X, the angle C here, must be equals to C plus 29, since only here is equals to 29 degrees. So we have angle C is equals to, angle C must be equals to X plus 29 degrees, and X equals to 40 plus 29, and that is 69 degrees. So similarly, we can look at this other part of the quadrilateral. I'm looking at quadrilateral DOAP, this other side. And I'm going to do a similar thing again by producing a line to meet the external point P from the center of the circle O. And of course, this line is going to bisect the angle 118 degrees. So let's say, since we don't have enough space there, so if we have each of these portion here is going to be 118 degrees divided by 2, meaning that each angle at each portion here is going to be 59 degrees. And here too is going to be 59 degrees. And don't also forget that this angle, this line, make an angle of 90 degrees just like before with the tangent SP. or HDP. And also this line, this radius, make an angle of 90 degrees also with the tangent PAQ. So what happened there is that since here is 59 now, and here is 90 degrees, that means it's possible for us to have the value of the angle here. So the value of the angle POA from the diagram, angle POA, angle POA angle POA must be equal to 90 degrees minus 59 degrees. And that equals to 31 degrees. Making us to know that here is 31 and here must be 31 as well. So making that angle ODC to be equals to 62. Similarly, it will be possible for us to find this other isosceles triangle. So this time, let's call this angle at the base here Y. So for us to find the value of Y there, we do a similar thing that we did for the X. That means 2Y plus X. You don't even want to do like that. Okay, 2y plus 62 degrees, not X, sorry. Must be equals to 180 degrees. That is sum of angle in a triangle. And what's the name of the triangle? Triangle OAD. And if you make Y subject of the formula, so Y will be equals to 180 degrees minus 62 degrees divided by 2. And that is still going to give you 59 degrees. Yes. Yeah. That means each of these places that we have Y here must be equals to 59 degrees. That's 59 here and 59 here. Okay. Um, that means we completely obtained the value of angle D at this point. So that means angle D equals to X plus Y. Look at it here. We have X here, we have Y here, making the full angle D. So X plus Y there, X is 40 degrees and Y is 59. So 40 plus 59 degree, that will be 99 degree. The next one that is left as very visible for us to obtain is the angle B. So for us to obtain the angle B, we will use theorem 1 of circle theorem, that angle at the center is equals to because we don't know whether this other line is really straight. Nobody really have an information about that. So I'm going to use this theorem. The angle at the center, or this reflex angle here, equals to 2 times of angle at this point on the circumference. You should be familiar with that theorem 1 of circle theorem. And the angle at the center there is 162, like 50 plus 50 plus 631 plus 31. So we have angle at the center equals to 50 plus 50 plus 31 plus 31, all in degrees. And that is 162 degrees. An angle at the circumference is angle B. So we said that for write the B, the angle at the center equals to 2 times angle at the circumference. So if angle at the center is given as 162 degrees equals to 2 times of angle B, that's the angle at the point B. That means if you make B subject of the formula by dividing both sides by 2, you have that B, angle B, must be equals to 81 degrees. And then, similarly, to obtain the last angle, which is this place, which could help us to find the value. Let's call that place Z. We can call this last angle Z degrees. So for us to find the value Z degrees, we are dealing with quadrilateral. That means angle C plus angle D plus angle B plus angle A must be equals to 360 degrees, sum of angle of a quadrilateral. So I will first write that. So angle A plus angle B plus angle C plus angle D equals to 360 degrees. Sum of internal angle of a quad. Sum of internal angle of a quad. And this is A we want to obtain right now. Since B is equals to, we have angle B is 81 degrees. We have A plus 81 degrees plus we have C and D 69 and 99 equals to 360 degrees. So we have to make a subject of the formula by adding all of these, or you just go ahead and say A must be equals to 360 degrees minus 81 degrees minus 69 degrees minus 99 degrees. And that will definitely give you, which is equals to this and this, that's 111 degrees. And I believe that was very helpful. I believe you understand everything. I just want to believe that you can, if you see this kind of problem, you'll be able to solve it very, very well. Please don't fail to drop your your questions on the comment section, and of course, subscribe to the channel if you have not done that. And don't fail to share it with friends, because it will also help your friend to go along. So to summarize all, it therefore means that in that diagram, angle A equals to 110 degrees, angle B is equals to 81 degrees, angle C is equals to 69 degrees, and finally, angle D is equals to 99 degrees. Thank you and have a nice day.